like to look at activation register records, and this gets a little bit complicated, so pay close attention. A subroutine is activated when called. And when a subroutine is called, an activation record is allocated or pushed on the stack. An activation record is a template of the relative positions of local variables on the stack as defined by the subroutine. This includes the return address, memory for local subroutine variables, those are the ones used in the local subroutine, but it also includes parameters passed to the subroutine from the caller on the stack, and registers that were saved by the subroutine, callee save, because those registers are used in the subroutine and the data in them would be lost if they weren't saved. A new activation record is created on the stack for each invocation of a subroutine or function. So whenever you call one, it makes another activation record. And so if you have recursive subroutines, you could have, use up a fair amount of the stack. A frame pointer indicates the start of the activation record. When a subroutine ends and returns control to the caller, the activation record is discarded or popped. In other words, we've used it up, and the stack pointer should be pointing where it was when you entered the subroutine. This is an example. We'd like to look at this example carefully. Let's look at the top there after the .c declares business that sets up the where the P1 dir is and the watchdog registers and all that. There's an equate statement, and it equates 50 over 2 to delay. So basically, delay is going to be a variable name for what we're going to start out with, where it's going to be initialized as 50 over 2 or 25. You can put all kinds of expressions in the after the equate for what it's equated to, and let the assembler do the arithmetic for you. You could have just put 25 here instead of 50 over 2, but I wanted to show you that you can put in, have the assembler do the arithmetic for you. Then we have the .text statement indicating that the subroutine comes right after that. And right after that, the first thing we do is we initialize the stack pointer. So we're putting it to the, starting it at the where the stack pointer is the basically the end of RAM usually. So for this MSP 430, it's at 0x0400. Then we stop the watchdog timer, and we make the port 1 bit 1, make that into an output with the data direction register for port 1. Then we have our main loop. So our main loop, first of all, it toggles port pin 0, the one we made an output, it toggles that. That's connected to an LED, I assume. And we're going to push immediate delay onto the stack. So what that does is it puts 25 on the stack, and it moves the stack pointer down 1. Then we call immediate delay. So if we look down further, you'll see the subroutine with a lowercase delay, and we're calling that right now. And so it's going to go down and start executing that subroutine. But before it does that, it puts the return address on the stack, and so we would have the stack pointer pointing at the return address, and then 1 above that, the stack pointer plus 2 address would be the capital DELAY, or 25 would be in that value. So yeah, then we get into this subroutine delay. The first thing we do is we push register 15. The reason we're going to do that is because we're going to be using register 15 in this subroutine, and so we need to make sure that we don't wipe out what was in register 15 if that was important to somebody else. So we're just pushing that. So now the stack looks just like you see there in the comments. The stack pointer is pointing right at a value of memory that has whatever was in register 15 when you called the subroutine. Then 2 above that is the return address that we'll go back to after the delay, and that's actually whatever the address is of that jump main loop thing that's right after the call. And then 4 away from the stack pointer, 4 bytes previous to that, is the actual value 25 in the stack pointer. Now it's actually kind of handy to see this in the integrated development environment, and we'll do that in a minute in a little video for you. So anyway, that's what the stack looks like. So the first thing we do after we push that R15 is we move immediate 0 into R15. So we're putting a 0 in the register 15. And then we subtract 1 from that, and after we subtract 1, we check and see whether we're back to 0 again. See, when you take 0 and you subtract 1, that'll give you all lefts, or -1, and it just keeps going around, and eventually, if you keep subtracting 1, it'll get back to 0, because remember, it was kind of a circle for, goes around and around and around. So you keep going in that little loop there. There's the yes and the no answer you can see over there on the right in the comments. And you go through that thing 15 times. Let's actually look at the little bubbles here. This the first one, which I probably should have shown you before, is basically how the stack is as soon as you push that R15. And so anyway, now the next thing that happens here, let's go back before that. Well, look at this. You keep going through this delay, you're going back to this delay too until you wrap around. And at that point, you see that subtract 1 from the 4 plus the stack pointer. Well, 4 plus the stack pointer is where that 25 was located. So now the 25 becomes a 24, and then you check and see if that was a 0. If it wasn't a 0, you jump back up to delay 02, and you go through that whole thing all the times you need to until it wraps around to itself, and finally, the 25 gets decremented again, and then it keeps, it's down to 23. It keeps going. Finally, it gets down to 0. In which case you pop R15. In other words, you grab the register, the value that the stack pointer is pointing at, and you put it back in register 15, which basically restores whatever was in our register 15 before you called the subroutine. And then what you do is you want to get the stack pointer. You want to move the stack pointer, whatever is in the stack pointer, which is the return address. You want to put that return address well, it's right now it's pointing at the return address, and it puts it right back in the return where the return address is. So it really doesn't change anything. That thing doesn't do anything. But then the return takes that return address that's there and pops it in the program counter, and it moves the stack pointer so that you're actually pointing that. You end up with a stack pointer pointing back at the place where you put delay before. And then it jumps back to main loop, and the whole thing repeats again. So let's look at the little bubbles here to see what they say. Basically, we're saying right here, after you pop the register 15, you can see that you have then the delay count and the return address, and then down here you just have the return address, and when you return, you're back to how you were to begin with. So that's an example of the activation records. In this case, the activation records are 6 bytes, and they contain delay and the return address and the register 15, the stored value from register 15. So let's look for a minute at recursive subroutines. A subroutine that makes a call to itself is said to be recursive subroutine. Recursion allows direct implementation of functions defined by mathematical induction, and recursive divide and conquer algorithms such as factorial or Fibonacci or summation kind of setups and other kinds of data analysis. Allows you to do tree transversal, binary search. Recursion really solves a big problem by breaking big problems into smaller ones and make the big one easier to solve. And it reduces duplication of code. And in order to do recursion, you must use the stack. So how do the addresses work when you're doing a subroutine call? So when you do a call, you call the subroutine, what happens? The syntax is call, and then you put the destination address in there. So the destination address goes into a temporary variable. The stack pointer is decreased by 2. The program counter goes into the new place where the stack pointer is pointing. In other words, you move the stack down so you could put the PC in there, and that saved that. And then you put the temporary address that you had stored in, it was your destination, put that into the program counter, and that pops the program down to the subroutine. So a subroutine call is made to an address anywhere in the 64K address space. All addressing modes can be used. So you can use immediate, that's the most common one, but you can also do all the other addressing modes, and we'll look at some examples of that. So you could actually make it so it calls. You can pick which subroutine it calls, based on one of those other addressing modes in a fancy way. Call instruction is a word instruction, and the return address is stored on the stack. Status bits are not affected by the call. Let's look at an example. So here's the call instruction. This is how you get into the subroutine. If you notice over here, the program counter is pointing at a place in memory, and that place in memory is 0x12b0, which if you look up, that's a call. And so it's calling, and it's calling 0x801e, which is actually the address of that func down there. So let's see how this all works. So you can look at the comment there, and it says, well, if you decrement the stack pointer a couple times, that memory gets used up with the program counter. In other words, we put the program counter in the next address on the stack and move the stack pointer down. And then we put the program counter in the memory that the function was pointing to, which is basically 0x801e. So let's see how this works. First of all, the PC goes out. It's pointing at that memory address, the memory in that address, the instruction. 12b0 goes into the instruction register that's decoded as being a call instruction. this program counter is incremented by 2, of course, and the program counter moves down. Then it grabs the place where you're calling. It needs to know where it's going to go to, the 0801E. That's grabbed, and that's put into the ALU. And then let's see what happens next. The stack pointer, or the PC, is as decremented, goes down and is moved down to the next address. This would be the address that's called after the subroutine is executed. And we put -2 into the adder, and we take the whatever the stack pointer was, and we add that -2 to it, and so we're decrementing the stack pointer, and then the stack pointer moves up, and then after the stack pointer moves up, the address that's in the program counter is stored on the stack, and then let's see. So then that's whatever the program counter was is stored on the stack, and then the next thing is the address that's in the ALU is put into the program counter, and the PC advanced down to the function that we're calling, and execution continues from there. So here's some examples of all the different addressing modes you can use with a call. The call, an immediate exec, that's what we normally do. There would be a label in your program called exec, and you call immediate exec, and that's going to go and actually start executing at that place you called exec in your program. That's the normal way of using it. But there's also other fancy ways to do it. If you don't put the immediate on there, it takes it's a call on the address contained in exec. So you can see what happens there. It takes the PC plus X, and it puts that in temp, and basically the only difference in all of these is what goes, where is the subroutine that's getting called. And I'll let you look at all of these different ones. There's all the standard addressing modes are possible. So what happens when you return from a subroutine? The syntax is RET. That's actually a pseudo instruction, but basically what happens is it takes whatever's in the address that the stack pointer is pointing at, the address that's in the stack pointer. The stack is pointing to a memory location. Whatever's in that memory location is stuffed into the program counter, and then the stack pointer is incremented by 2 memory locations, which is really making the stack go down by 1 position. It's 2 memory locations because they're bytes, and you have to go, everything moves by words on the stack. And so the emulation for the return is move the whatever's in the stack pointer to the program counter, and then increment the stack pointer, and you can see it right there. That's what the return thing does. So the return address is pushed onto the stack by a call instruction and is moved to the program counter. The program counter continues at the code address following the subroutine call. That's what was stored on there previously. The status bits are not affected. So here's an example. This is similar to how we looked at the call. Let's look at how the return works. So basically, it's the instruction it's doing here is move.w, whatever's in the stack pointer, to the program counter, and then increment the stack pointer. So we start up basically where we left off in the subroutine. We're assuming that basically all this subroutine had in it was a return of 4130. And that's that move instruction, which is basically the pseudo or the real instruction for the pseudo code RET. So first of all, the PC tells us to go out and grab that number 4130, put it in the instruction register. It's interpreted as this move instruction, and then the program counter is incremented by 2, which moves the program counter down, and we take 2 and we put it into the adder. The stack pointer is added with that 2 to increment the stack pointer, and before we grab what's at the stack pointer, put it into the ALU. The stack pointer adds the thing, puts the new points to the new location on the stack pointer. The PC moves down because it was incremented, and finally the ALU feeds the value that was the right under that 0x801E, that whatever address that is, goes into the PC. The PC now points up there to the address right after what it was, the call thing, and then you go on from there. So here's a little tricky quiz for you. This would take you some time, and I would suggest, it actually would be good for you to use the integrated development environment and actually your board to make sure that your code actually does what you want it to do. So that's the end of this video, but there will be a video on actually setting up the integrated development environment and using it, and hopefully I'll make a video on subroutines so you can actually see the things happening in the IDE, and then you can try it yourself in your own integrated development environment. The IDE is a great learning tool.